Deadlock is an important concept we should know about when we are writing multi-threaded code in Java. Let's learn about the same. What is a deadlock? Here is an image which tells us about a deadlock situation. Let's have a closer look. Here we have two threads which are running. Thread 1 at some point of time is going to need lock A, which is represented by a green color. Then after some point in time, thread 1 is going to need lock B, which is represented as blue color. Now let's look at thread 2. This thread is going to need lock B at some point of time, and then it's going to need lock A after some time. Please note that in both the threads, both the locks are needed to be acquired in order for the processing to get completed. Only after the processing has been completed, both the locks A and B will be released. Let's imagine this scenario at time t. Thread 1 needs lock B while it has already acquired the lock A. Likewise, thread 2 needs lock A while it has already acquired the lock B. But both the threads won't be able to acquire the needed lock because their need is being held by the other thread, and neither of the threads are in a situation to let go of their acquired lock since it's needed to complete the processing of the thread. So in this situation, none of the threads could proceed with their execution, and this situation is called as a deadlock. So here is a formal definition of the deadlock. In a multi-threaded context, a deadlock occurs when two or more threads are blocked forever, each waiting for the other thread to release a resource they need to proceed. This situation creates a cycle of dependencies with no thread able to continue with its execution. So how can we spot deadlocks in our code? There could be two approaches. One is the manual approach, other is the programmatic approach. So let's learn about the same. Well, detecting or spotting locks at the compile time is not an easy task. This is so due to multiple reasons. Java comes with multiple types of locks, so multi-threaded code can be littered with different types of explicit and implicit locks. Also, there could be multiple sources of threads in the code base. Due to these two factors, combined with the fact that the thread execution and CPU allocation is not deterministic, it's nearly impossible to figure out when which lock is going to be acquired by which thread. Moreover, the example we saw earlier was a simplified version where we had two threads and two locks. However, in real world, it won't be this simple. There is a good amount of possibility to have multiple threads and multiple locks, which could lead to a deadlock situation. And thanks to all of these complexities, it's nearly impossible to detect a deadlock by just looking at the code. So the manual approach is something which is not very efficient, neither it's the suggested approach. So how do we detect the deadlock in code? Let's have a look on the programmatic approach of detecting the deadlock. So now that we have learned that detecting a deadlock is very difficult in manual way, are there any other tools which can help us in this detection? Good news is, yes, there are tools and ways in which we can detect deadlocks in our code. Two of the most common approaches are taking the thread dump and uses of the thread mxbean to programmatically detect cyclic thread dependencies, which can lead to a deadlock. So let's have a brief code demonstration where we will be knowingly introducing deadlocks in our code and then use these methods to detect the deadlock situation. So in order to demonstrate the deadlock code, I'll create this package and let's call this package as other concepts, and let me create this class as deadlock demo. We will have two locks, so lock A, and make this as a reentrant lock. Let's duplicate it, create another lock B, and we will have two methods. First would be a worker1 method, other would be worker2 method, and let's implement these. So public void worker 1. It will start by acquiring the lock A, and then there would be some message which will be printed like worker 1 acquired lock A. Next, we will introduce some sort of sleep time. So let's call thread.sleep for 200 milliseconds. Let's handle the interrupted exception. Let's throw it as a runtime exception. And then we acquire lock B. Then let's print some message. It could be something like worker 1 acquired lock B. And then we start by unlocking the locks, which is lock A dot unlock and lock B dot unlock. So this should complete the first method, which is worker 1. Now we will duplicate this and we will write the worker 2 method implementation. What worker 2 does is it starts by acquiring the lock B, and then we will of course change the messaging here, and again we have a sleep for 200 milliseconds. And now after lock B is acquired, lock A will be acquired, and again we will adjust the messaging, and then we can have lock A unlock itself and lock B unlock itself. Now let's write the main method where we will be creating the threads and executing these things. So we start by creating the object for the class so that we can invoke the methods. Now what we can do is we can say new thread demo dot worker 1. We will give this thing a name, this thread a name, and we call dot start. Likewise, we'll create a thread which will be making use of the worker 2, and we will adjust the name here for the thread which will be worker 2. So let's run this thing and see what is the output like. Alright, so what we see is worker 1 has acquired lock A and worker 1 acquired lock B. So essentially the worker 1 got a chance to run, and after that point of time worker 2 was supposed to be run, but now we are in a deadlock situation because worker 1 has acquired the lock B, and here worker 2 requires lock B in order to do its processing. But since the worker 1 has acquired lock B and not released it yet, the worker 2 cannot get hold of it, and that is the reason we have entered into a situation of deadlock. What we can do about it now? Well, in such cases you cannot do anything, but your code will be sort of in a deadlock situation and you will have to terminate it. So as told earlier that we can either take a thread dump, or maybe we could use the other approach of using the thread mx bean to understand what part of the code is leading to this deadlock situation, right? So let's understand the first approach, which is using the thread dump. So what we will do is we will go to the terminal. So let me come out of the distraction free mode, and here we go to the terminal, and in the terminal we will list all the processes which are running Java. So we see that these are the processes, and the one which we are concerned about is this deadlock demo, and here is the process ID. So what we do is we call kill -3 and we pass the process ID, which is this one. Hit enter and go back to the output console. So here we can see that we have lots of messages which are getting printed. So this is something that we had earlier, right, where we had the deadlock situation. Now we are seeing something called as a thread dump, which is the full thread dump, and it's going to show certain information regarding the thread classes, certain messages, and so on and so forth. Of course, you could try to do it yourself on your system and read through all these things, what exactly is being told. But the most important thing is in the last. So scroll to the last, and here we have this message, and this thing says that found one Java level deadlock. What does it say? It says waiting for ownable synchronizer, a fancy name for the lock, which is held by worker 2. So worker 1 is saying that it's waiting for a lock which is being held by worker 2, and the worker 2 says it's waiting for a lock which is held by a worker 1, right? So what you could do is you can scroll further down and you could see that this is one line which is being hinted in your code. Click it out and you could see that this is a probable reason. So in your use case, in your real world use case, whenever you are faced with this kind of situation, this is the way in which you could find out the process ID and kill it with -3 as the argument, and this will help you out with this thread dump, and you could figure out, at least you have a point of investigation where you could try to understand what is the deadlock situation and what part of the code is leading to this scenario. So this is the approach in which you could analyze the thread dump to understand the deadlock. There is another approach, however. So let's go to the code and we will have to modify something in our code in order to understand that particular approach. So what we are going to do is we are going to make use of this thing called as thread mxbean, and we will create another thread, let's say a thread 3, which is going to execute forever, and it will be done after an interval of every 5 seconds. So the idea is to probe the code and to understand if there are any threads which are in deadlock. So let's write the code. It will be much simpler to understand that way. So let's start by creating a thread, and let's supply the code for the same. So the first thing is we have thread mxbean. Let's call this as mxbean, and it provides a management factory using which you could create the thread mxbean, and while true, what we can do is we can say mxbean find me all the deadlock threads. It will return a array of long, which are basically the thread IDs, and if the thread IDs does not happen to be a null, so we can print this message that deadlock detected, and we can iterate over the long thread ID for each of the thread IDs in the thread IDs, and then print this message: the thread with ID, thread ID is in deadlock. And once we have printed this message, what we need to do is break out of the infinite loop, and if that is not the case, so we need to do this every 5 seconds. So let's put a timer of 5000 milliseconds and catch the interrupted exception, and we will throw it as a runtime exception. And finally, let's call the .start on this thread. So here is what is happening. We have created a thread which is going to run every 5 seconds, and we are making use of the management factory to get an object of the mxbean, and the mxbean has a method which will give me the deadlock thread IDs if there are any threads which are in deadlock, and I am simply going to iterate over the given thread ID, right? And print the message here. You may be wondering that thread ID is fine, but what if I need certain extra information? How can I do that? Well, there is another method in the threadmx bean which is called as get thread info. So let's make use of that as well. So we can say mx bean get thread info, and it's going to accept a long array which is the thread IDs, and what it returns is an object of thread info array, and let's call this as thread info. So thread info contains a lots of information, as in what is the thread name, what is the lock name, where exactly it is waiting for which lock, and all those things. So in this example we don't really need to showcase all those things. So but the idea here is that if needed, you could certainly make use of this particular line and iterate over the thread info and get the required information. So let's run this and see the output. So run, and initially we have executed these threads. There is a timer of 2 seconds, remember, 2 milliseconds rather, and then after some point of time this thread kicks in and it's going to say thread lock detected, and thread with ID 21 is in deadlock and thread with ID 22 is in deadlock. And as I told earlier that if you need certain more information, you could make use of the thread info object or the class, and these are the information it contains, and you could make use of this information in your code as per your need. So now that we have seen the code demonstration for the deadlock, let's understand how can we prevent deadlocks. So are there any approaches or suggestive measures using which you could get rid of the deadlocks, or at least try to write a deadlock free code? So the first and foremost is use timeouts. So let's say when your thread is trying to acquire a lock, giving a timeout will ensure so it's not going to end up into a situation where it's trying to acquire a lock for infinite time, right? And thus it will help in avoiding the deadlock situation. So uses of timeouts is a good approach in order to avoid deadlocks. The second thing is the global ordering of the locks. So another thing we can do is to pay attention to the global ordering of the locks. What it means is, let's say we have 2 threads and 2 locks to acquire, for example lock A and lock B. Both the threads should first acquire lock A followed by lock B. So in that sense it won't be a cyclic dependency scenario and it will avoid the deadlock situation. The third thing is to avoid any sort of nested locking. So whenever feasible, we should always avoid locking within already locked section. And the fourth preventive measure is to make use of the thread safe alternatives. So whenever feasible to do so, use thread safe collections and atomic variables and minimize the uses of locks. Sure, the thread safe collections do make use of the locks under the hood. However, in general, the code implementation of the standard thread safe are battle tested industry solutions. So there is a little to no chance of running into the deadlock situation. So this should be it for the concept of deadlock, and these are the certain measures using which you could try to avoid deadlock situation. And even if you are in one situation of a deadlock, what are the different approaches using which you could analyze your code to correct it.